23 March 2023. Breezy afternoon, a bit rainy. Spring. I figured I'd pick up where we left off a bit in chapter 2 of Maugin's book on nonlinear electromechanical effects and applications, about the development of the nonlinear contribution to the wave propagation equation in the setting he's defined as to where with various particulars held constant and establishing a central milieu of what are the essentially linear constituents of the electrical and magnetic fields, and in terms of heat and the thermo, and then for the piezoelectric and the kinetic and acoustic, according to the acoustic Christoffel tensor and these various settings, that then he's so arrived at a description of what there is an introduction of at least some of the nonlinear components, if not all of them, that he's defined this as what results a sort of box that he called the monomode process, where what we had reached was the definition of the monomode process with regards to that it encompasses some of the nonlinear contributions, what otherwise are in effect only the partial, or after Hooke's law, when we talk about the linear constituent in the continuum equations and relations, that Maugin's development of the monomode process here, or his allusions to it, as so developed from their originarity, that it so arrives at that more is to be said or less for what's said. So to that end, let's see, these other books here I'd set aside were Theory of Thermally Induced Gas Phase Reactions. Thermally induced gas phase reactions. Get into discussion. We had mentioned earlier phase in terms of the phase of electrical current, and alternating current and direct current are two interesting notions of how electricity moves in our fluid model of electricity, and how they are not like Newtonian liquids and other elements in that what's called phase of the usual notion of the solid, liquid, and gaseous phases of materials according to their melting and boiling points and their enthalpy of fusion and what happens when they precipitate, in terms of how they change phase, vis-a-vis something like what's called the triple point of steam and live steam, when again, empirically, these phase transitions also have, according to conditions of pressure in the Newtonian and non-Newtonian liquids, about how there's such a notion as the live steam. And kind of as a reference to there was earlier about the logarithmic tables, and about how those were used as an assistant to computation for hundreds of years as an industry, that the steam tables are not just a lunch counter, but rather help represent, according to various conditions of what are machines that involve the steam engine, and other uses of steam and live steam for work, and steam and live steam and steam and cold steam, that this water vapor under pressure is very particularly well known in terms of its fluid models and its liquid models and its eddies in its currents and the vorticity and turbidity, as we might call it, in terms of then these various models, how they relate in terms of other physical media and the media of charge, or the quantity of the electron, that in terms of the force carriers, when we get very fundamental and talk about the field theory and the parallel transport and the soliton and the sonons, phonons, and other notions of discrete amounts of energy in terms of measurement, sampling, and observer effects, that it's so arrived at this thermally induced gas phase reactions reflect how the effect of anharmonicity and rotational active degrees of freedom point back to why oscillation, harmonicity, and anharmonicity and such things refer to our isotropic and anisotropic systems of continuous transitions, or transitions in the continuous over discrete boundaries or across well-defined surfaces, in terms of, as the author puts it, the earliest theories of the thermal decomposition of a diatomic molecule. And as we were talking about atomic chemistry and molecular chemistry, and thusly our organization of the consideration of the bonds of atoms to each other, which form molecules and polymers and such constituents of the demarcatin and chemical, and what's called the surfaces of these things, in terms of our continuum mechanics, particle mechanics, surface mechanics, in terms of various quantities defined usually in the thermal, like pressure and temperature, and their proportional equations and inverse equations, or as inverse and proportional on the various orders, like inverse square, inverse cube, as they are related to such things in terms of the diffusion as over an area or a volume, and these types of things. That as we look at that, and that this is Norbert Wiener's the human use of human beings, cybernetics, and society, where he talks a bunch of years ago about what's his outlook on the future. Not so much related. That this kind of text, Nikitin's theory of thermally induced gas phase reactions from the Academy of Sciences of the USSR, translated by Scripta Technica Inc., from Northwestern University out of Indiana University Press in 1966, it describes what's going on in chemical kinetics from a microscopic molecular viewpoint. That being the assembly in the harmonics of the above the wave, the resonances, the molecular reactions, vis-a-vis our most fundamental and independent and elementary atomic reactions. So back to Maugin. The bookmark is at page 45. And we had just read, this corresponds to the working hypothesis of a monomode process. In this condition, only terms corresponding to alpha beta equals gamma equals delta in equation 2.18 are kept, and the latter equation takes on the simple form, no summation over alpha, of the rho sub r u umlaut alpha, and then subtracting that term, establishing that it's the difference, and makes sense for a boundary, that it's the sum of what are these zero terms, or how the term is defined as what vanishes, as it were, the gamma and the delta in the second and third order. So we continue. If we're given alpha, equations 2.15 and 2.20 can be simply written as rho sub r u underscore tt minus the gamma u underscore xx equals 0. So this reflects kind of as a reading further ahead that those terms are what they're defined according to their quantities, that according to the conditions of the continuity equations, they're so established as an identity about 0. Now, oftentimes when we say identity as an equation, what we mean is that something equals 1. Sine squared x plus cosine squared x equals 1, for example. And all what results of the formulas and other identities are in terms of basically that the algebraic quantity on either side is 1, or unity. So here when we start talking about these formulas and identities and equations with respect to that's in the multiplicative, and after the definition of division, say first, when you divide division before multiplication, taking parts before adding them up in the modular, that here it's that's about the multiplicative identity 1 and how algebra works on either sides. You can divide both sides by either quantity or multiply both sides by either quantity. That then this identity, as it were, is about the additive identity 0 instead. that the subtraction of what's otherwise this term with what's been boxed out and after the contributions and what establishes this case for a minimal error term, that equation 2.21 reads rho sub r u underscore tt minus lambda u underscore xx equals 0. And rho underscore u underscore tt minus lambda u underscore xx equals gamma quantity u sub x squared x sub x plus delta quantity u sub x cubed quantity sub x. So here he is establishing that both these quantities, both these equations, both these conditions hold over these various surfaces as gamma and delta have been defined in terms of the earlier definitions of what are these constraints or what's hold fixed earlier, that we can so arrive at that this is so. And as he continues, where the subscripts t and x simply mean partial derivative with respect to time and space material coordinate respectively. Equations 2.21 and 2.22, which were just read, these identities for an additive identity, where the quantities can only observe where it works out that it's the additive identity reflecting 0, the middle of the continuum, whereas in the multiplicative identities, it's instead that after a phase transition or reaching a limit towards 0, that 0 is the multiplicative annihilator. The equations 2.21 and 2.22 are the equations of one-dimensional, in the abscisse, linear and non-linear motions respectively. Thus he's established that first, that the usual linear case, after it's neglected these other components, he's just simply establishing that these higher order components are so bounded that they're the second and third order terms respectively, as he so then establishes that their rank and ordering, that when they instead blow up or dominate, that you could read as to why the nonlinear effects are as in effect over what is otherwise that the linear terms have a vanishing nonlinear effects and result that the identities and equations hold true. So in this setting of a balance of them together, they can also be written as u underscore tt minus gamma over rho r u xx equals 0. Here it appears he's taken an algebraic transformation of the formula and inverted some of the terms and basically written that if something equals 0, its inverse equals 0. Similarly, as that if something equals 1, its inverse equals 1. Or here is rather that the inverse operation is subtraction. Obviously that division by 0 is the only thing that is not closed in all of arithmetic, except for addition to infinity. In addition to infinity and division by 0, and their reciprocals, multiplication by infinity and subtraction of infinity, are not defined. Otherwise, that all arithmetic operations are closed. So that reads 2.23, a rewriting of 2.21. And u underscore tt minus u underscore xx of this bracketed quantity, gamma over rho r quantity times the quantity 1 plus 2 gamma over lambda, excuse me, that was lambda over rho r, 1 plus 2 lambda, 2 gamma over lambda, u sub x plus 3 delta over lambda u sub x squared equals 0. Here he's established that he's just taking that if the derivative after the chain rule results that is taken out as that part, that he's just factored out that the quantity of the main, which is the lambda over rho r, this ratio, that otherwise he's just extracted what are the terms that after partial differentiation fall out are left over as this polynomial in u sub x, and that its coefficients are 3 delta over lambda, 2 gamma over lambda, and 1, the linear part. The latter equation is of the form u underscore tt minus u underscore xx g, where g is a usual formula introduced as a substitution for a formula, otherwise f, formula or function. U underscore tt minus u underscore xx g of quantity u underscore x equals 0. He's replaced the term described as the factoring and the representation as after the partial as a new function that he's substituted into this equation and defined it as g. An often studied equation corresponds to delta equals 0 in equation 2.24. And in the above, that would make it thus that the contribution of the second order term was also 0, because delta is the variable of the coefficient of the second order term, which was the third order term reduced one term by differentiation. With the appropriate non-dimensionalization, we obtain then u underscore tt minus u underscore xx of the quantity 1 plus epsilon u underscore x equals 0. Thus that he's basically defined that there's and I'm not familiar yet with the action non-dimensionalization, although I imagine it would reflect as to earlier in the discussion of the abscissa, and that the dropping of the ordinates is establishing a bounds and a box or a sphere is about the outside of a thing, that this non-dimensionalization is sort of taking that back, and it results a way to, again, result a linear and something that's tractable or not, as we've been discussing, by algebra, this equation or relation or formula as a function, where epsilon equals the ratio of third order elastic constant to second order elastic constant may be considered as a small parameter. Here, the notion that something is small is that on the order of it, any linear constant times a small constant is yet small. And in fact, it's established that according to its order and rank, a higher order component, according to the coefficient of the higher order component, as long as it's small and not bigger than the component is rank, it won't be twice as big or bigger than the square of the higher order rank, and thus that the middle term is yet proportionate to the higher order term. Thus that they're kind of bounded together. Equation 2.26 governs longitudinal wave propagation in an elastic bar. So this reflects that according to these other quantities, which would also have their restitutive effects or otherwise that share the same milieu for the same displacements according to the same configuration space, that equation 2.26, to repeat, governs longitudinal wave propagation in an elastic bar. Simple mathematical results concerning its solution, as well as solutions of equations such as 2.26 but involving higher order derivatives, are given in appendices 2.8.2 and 2.8.3. Here below we shall study equation 2.25, which was the rewriting of the term with the function defined as g, reflecting the reduced terms, having drawn out that the derivative was proportionate to the partial derivative, or rather its derivative in u sub x, that those conditions hold as to where the linear input is proportional to the linear scope, it would seem. So that ends section 2.1, and having read that a minute, I'm going to look ahead a little bit and see what the next section says. 2.2 is solutions by means of the method of characteristics, simple waves, etc. So characteristics refers back to our linear algebra, and there's much to be made of the mention of the linear algebra in the setting that that's where matrix theory comes from, that's where the theory of determinants comes from, that's where systems of linear equations are put into play, that's where otherwise including solutions of polynomials arise. That's where we have Gaussian elimination, that's where we have matrix decomposition, and a lot of other things in terms of that by making a rectangular or square array of numbers and transforming them in given particular ways, that their conjugates arise, that their product transformation rules are developed, that the tensorial quantities and vectorial quantities they represent so exist, and their products are well defined about their inner and outer products, as so discussed and mentioned. that it's really kind of a scratch pad, that matrix theory is kind of anything to do with a rectangular array of numbers, that really these are only particular weighted results that kind of come up in terms of, then the characteristics usually reflect a notion of the solutions of polynomials, and that the characteristic functions and characteristic polynomials reflect that according to the roots of these polynomials, that some of these results from the linear algebra, which is any kind of operator theory on usually what can be represented as matrices, which can be matrices of complex numbers and or matrices of block submatrices and that these the solution he describes or would read out goes in section A, and transforming into a system of equations, that each equation involves differentiation in one direction only. So he's assuming a way to scratch an orthonormal vector basis on the thing. That he goes to reads and makes a development and describes what are some characteristics and outlines some solutions that will fulfill each of these. That then he finds some what can be read off as constants after integration, or for regions of integration, after differentiation, and for regions of integration, that since all characteristics C plus below C naught plus corresponding to epsilon equals 0 start on the x-axis with E equals V equals 0, and on account of the boundary condition 2.35, which is defined as an exponential integral, or rather with respect to an integration of a small area in terms of that same variable, where he's parameterizing the integration by its own variable. Kind of like when we have a differential function that's defined by a differential. This is the boundary condition he's arrived at, so that's quite curious. And on account of that boundary condition, we find that f tau equals phi tau, and thus a solution, E equals psi inverse of negative V. If instead of 2.35 we impose a displacement of u 0 comma t equals phi t, again kind of putting in what's expected to be in a sense, and so establishes kind of arbitrary condition, basically saying that as long as nothing moves it out of place, that it's not necessarily so stable otherwise, that this linearization or small angle approach is a numerical method of sorts that would result, if we were to break it out and break it down, a family of approximations. Then he writes that 2.41 will be the solution will be replaced by the solution as a family of functions. It's a formula in terms of the derivative of psi, phi dot, which is phi with respect to t, its derivative, of quantity t minus x over ce, the other solution. So here he's established some symmetries or relations that only hold according to these things. And he says this is an exact solution, but this solution is not so much convenient because it is an implicit solution. In this manner, we have to, or I have to look back and better refresh and recall my memory of what are the exact definitions of exact with regards to solutions, and with regards to the implicit and explicit solutions, which are basically in terms of the indefinite and the definite, and in terms of that they may so well vary in terms of that. Sometimes in dynamical systems, what's called the behavior of different systems of equations according to varying and varying only by a small amount in the initial values of initial value problems and boundary value problems, the tempest in the teacup is what's called chaos theory. And that chaos theory is a subset of dynamical modeling, and that basically chaos theory was renamed dynamical modeling. That chaos theory defines various things similarly to how there are systems of dynamical flows that are like attractors and repellers in terms of when things flow to a central point or they flow away from a central point. That in terms of flow mechanics and the branches and the eddies and the divisions of things, about how those are. he establishes a condition about, like, imagine if the C naught equals C where E equals 0. And then he takes the expansion because in the expansion these terms would drop out, and that then so results that he can rewrite the derivative with respect to Leibniz's notation in terms of the inverse of the negative of this constant, which makes it very tractable for arithmetic, as you could imagine, because it's as simple algebraically as you could replace it anywhere else with something that's just the inverse according to multiplication and the inverse according to addition. Hence it follows from velocity, from 2.42 velocity, which is that derivative with respect to time, from the implicit relation ... that then he's expanded and broken this up and broken this out and put out a few first terms of the equation that's the solution in terms of phi dot. So that would be 2.2, and so he describes that as a system of solutions, about the exact solutions and the implicit ones, and then he trails off with sort of what he's left off, but at least basically so indicating that according to at least some of the terms, that some of the values are so convergent that their initial terms of their expansion are significant as to what contribute enough value as that it can be read off as a value, and that it's so computed as a value. But now then he'll introduce in section B, near field solution. Section C, case of a sinusoidal excitation. This is again where small differences make a difference. And then in D, the far field solution. And about a uniformly valid expansion. And he mentions again implicit, exact, uniformly, where uniformity is itself a thing that is variously reflected and expressed in given systems of boundaries. About the far field solution in the breaking distance, BREAK, breaking as in broken, vis-a-vis breaking, BRAKE, breaking as in Brahms-Strelong or breaking radiation, slowing of the solution in the far field. He refers to S. Fubini, Giron, anomaly nella propagazione di onde acoustiche di grande ampiezza, anomalies in the propagation of sound waves in grand amplitude from alta frequenza 4, quattro, in Italian, of 1935. That he's given this setting about for the far field, and we look back to Hooke's law in the near field, and here for the far field, and the resonances, expanding 2.55 and Fourier series, where Fourier is our great man from taking cosine and sine and representing these things out as about Fourier series, and there's the Fourier transform vis-a-vis separately how that goes in the development of Maclaurin and Taylor series often, that he introduces up to the description where particular systems of coefficients arise in the resulting expansion, that the Bessel functions are introduced, where the Bessel functions name a function on integers that in various things, kind of like Pascal's triangle, at each row of the triangle represents the coefficients after the binomial theorem, or x plus 1 times y plus 1, or x plus 1 squared. The Bessel functions in these categories fall under a sort of what are called the special functions, but really after something like the Stirling cycle numbers and the Stirling subset numbers, then there are Bessel functions, and these are what are coefficients of these expansions. About then that it is built of an infinity of multiple harmonics of the fundamental vibration psi with amplitudes which have a pseudo-periodic behavior along the propagation direction. So here we have some somewhat underdefined terms called infinity and the pseudo-periodic, that it so defines that there's described that the harmonics in their construction attenuate and dissipate or attenuate all the way out to infinity in how they are restitutive or add back up to the fundamental vibration as what results a wave. And as in terms of these representations as sums and differences of sine and cosine with various periods, with various amplitudes, add up to be able to reconstruct any signal according to the Fourier transform and signal theory. Well, that's of interest. And then just carrying on a bit, just reading that up to section 2.3 is the solution by means of approximation methods. And he talks about the perturbation method of Poincaré, straightforward expansion. And so that's something to follow us from small angle approximation or linearization or the hypothesis of small perturbations. And what with regards to then making expansion of that, about the terms and the corrective terms in terms of the error terms, and after approximation, that any approximation is only coincidentally perhaps the accurate true value and precise, that the error term associated with any approximation is non-zero, that corrective terms are basically a reflection of that when it's so demonstrated that following terms of the expansion or the truncated terms of the expansion are discarded, that it's possible to so represent them approximately again in terms of a method of Poincaré. And we talk about Newton and Newton-Raphson and Newton-Coates, and then up to what's called Runge-Kutta in terms of how we have numerical methods to compute the value of a derivative or integral when we don't have an exact symbolic calculation, that these are well-known numerical methods besides then, for example, we have such as the small angle approximation where sine x equals x when x is small, and the linearization, which is similar in as above methods when it's possible to define that the error terms are bounded, and so that by replacing the error term with the term so bounded that the resulting approximation is as so bounded. And then the section B of that is the multiple scale technique, and that's a later emphasis in this work from what I understand, and I've been leafing through this before, but this is to be read here, that section C is the method of coupled amplitude equations. He's describing these various methods in mathematics that arrive at various numerical methods that are variously defined in terms of any kind of algebraic approach, any way you can manipulate the formulas and their contents as quantities according to algebra, that these are various numerical methods that exist and are applicable to any purely symbolic algebra of variables, quantities, that then have only various applicability in the applied, whether or not they maintain conditions such that all these conditions, as we've been discussing, that Maugin establishes to keep his frame rigid or to make linear and make his projection fall to the abscissa coordinates, and these types of things, or the non-dimensionalization, so result held up. And then section 2.4 is nonlinear vibrations of resonators, and so then that's kind of a step up when we get above the harmonics to the resonators, and that resonators are basically when harmonics are enclosed in a sphere or a area of resonation, that then instead of those attenuating all the way to infinity, that the resonator is contained in what's a wave. So we'll talk about that a bit, what a resonator is in terms of then the near field and the far field being when it's an uncontained resonator and it reaches out towards infinity. And then he describes some devices and some empirical formulas and diagrams some charts showing typical experimental curves, relating them to the parabola and other well-known things to do with the saddle and other well-known shapes that can be considered after dynamical modeling in chaos theory. Intermodulation, where modulation represents that which is modular, like the power, like the multiples of 2 are modular, the multiples of 3 are modular, the multiples of 4 are modular. Modular arithmetic. terms of the modulus. Then also the bulk, where we also have a clock arithmetic in our numbers, besides field arithmetic in our numbers. And then he ends the chapter describing that the experiment gives a value which is 50 times lower than the value obtained for quartz. So he's just describing that according to what we have here, here's an example of a particular experiment where an anomaly, it doesn't match its name, that the value computed, the anomaly is on the order of 50 orders of magnitude. So that's to be read some more later. I'll just leave the bookmark where it was before the characteristics of the nonlinear wave equation, as where that's used to develop the later near field and far field solutions, and that there's various definitions going that. There may be other ones. This might be a near field solution and a far field solution. There may be other ones in terms of the definitions, the derivations, and all what's relied upon from Fourier analysis and what that gets into phase. And then what we might consider in the world of after gradient, then there's what's called principal component analysis, which is where a given surface might have a gradient in one direction, but when you look at it, it has three competing directions. According to principal component analysis, it has three, whereas the gradient has one. The principal component analysis is another great and powerful tool, for example, to compute the gradient in linear methods. That principal component analysis is indeed, after the computation of the gradient, one of the most relevant things in terms of tools, and that is not so often addressed, where these methods are often designed instead in terms of mathematical functions according to formulas and tables, according to, for example, a wonderful book called The Handbook of Mathematical Functions, today called the Digital Library of Mathematical Functions, which contains, issued as from the government and Abramowitz and Stegen, the authors, as it's called, the Abramowitz and Stegen Handbook of Mathematical Functions, that those sorts special functions have presented and provided all sorts their analytical solutions and also sometimes tables of the values, because eventually these numbers need to be crunched. So that's the reading today from Maugin's development in linear, and as to where we talked about after the description of the linear and nonlinear wave equations, then there was reading off how he performs some various algebraic and differential transformations or manipulations of these functions and their formulas and identities, resulting identities, and as was discussed, that their identities about the additive identity, 0, and identities about the multiplicative identity, 1, and then for most people those are always free on any system and series of equations to add or multiply any equation by any value, as long as it's both sides, and as long as for division it's not 0. That he's establishing here, though, that it says about where, according to this, that you can't perform division by this identity, which is 0, for example, and you can't perform multiplication by the identity, which is 0 either, without resulting that it's necessary to then stop algebra from carrying on further after that, or referring back to the ex fossil quadlibe and that kind of thing. Or when usually one of the first proofs that people are given that has a subtle defect and that they're to analyze is along the lines of that it was introduced according to algebra that there was division by 0, thus that 1 equals 0. So that is not to be allowed, of course. But whereas otherwise, the total freedom of algebra itself is one of the greatest things when people learn that they can cancel first above and below the divisor bar. And when you have two terms of above and below the divisor bar and you can cancel like terms in like orders, that's great. Secondly, when you have an equation and you can perform algebra on both sides of it and thus transform the equations, that's great. And then when we get into these identities, like log E equals 1, or the natural log of E equals 1, or cosine squared plus sine squared x equals 1. That those then become very definitely relevant to the toolbox of tools to manipulate equations and formulas. Here then, that when we look to Maugin's introduction of how some of these formulas, he introduces that the terms are reformulated in terms of one of the parameters, thus making that there's some kind of implicit condition on the exact solution, that it is so that there must be some other means to guarantee that that parameter is held so parameterized according to some other system in time. That gets into what's called the reformulated. When, for example, you introduce a parameter in terms of its own parameter, and we might even look at that in some fundamental developments of how differential analysis is carried out, that this notion of a reformulation is a self-parameterization of sorts, or a exactly how the differential is defined as the differential is its own antiderivative or something like that. That here it's that the parameter is its own parameter or something along those lines. This is just a couple of these curious facts about the development that then carry on then in terms of what arises as following the application of all sorts analytical methods, including the introduction of numerical methods to compute approximations, to compute approximate values according to these formulas given the inputs. Then it will also follow that we'll see that Maugin has quite a serious toolbox, and that out of his kit there's much to be determined about not just what's applied, but how it's applied, and even when we apply something earlier in his development, apply something later in his development, that it's possible to rewrite much of the entire derivation given only the implicits from the beginning, if it becomes necessary or as it's so sound, in terms of other methods, as were mentioned. We're here, of course, in Maugin's toolbox and toolkit are very, very usual and regular tools of numerical methods and Fourier and Maclaurin and Taylor, and of geometries, trigonometry, and these sorts of things, and Poincaré, that then we'll carry forward some more about later, how these derivations are so following carrying out. So with that said, well, this has been the reading for today. And here we are looking again at multi-beam interferometry of surfaces and films. Let's pick a random quote here. Mica. Mica is a naturally found material with some interesting properties. Step heights on the mica, on the replica. The results. Here in his other Dover science books, we were discussing, there's Norman Campbell writes a What is Science? Martin Gardner, who's most famous for his contributions to American Mathematics Monthly or some other popular magazines, has written hundreds and hundreds of articles on mathematical games. He wrote an article for a while after mathematical games, the metamagical themes of Hofstadter were written up. But Martin Gardner I found very engaging and quite friendly and very nice. Physics, the Pioneer Science by L.W. Taylor. The Evolution of Scientific Thought from Newton to Einstein by A. D'Abro. Chance, Luck, and Statistics, the Science of Chance. Here there's discussion about probability theory. Basic Electronics. I got most of my basic electronic books from a book called Electronics 1.7 and from Radio Shack pamphlets. Basic Theory and Application of Transistors, Guide to the Literature of Mathematics and Physics. I learned much about my theory of transistors from a book about vacuum tubes. I have a dictionary and catalog of all what vacuum tubes existed before the transistor was invented, where a vacuum tube is a very particular sort of application of the electrical field in a vacuum according to the anode and cathode and various combinations thereof, according to the Hall effect and various gratings and these sorts of mechanical constructs that make for it's possible to use power electronics instead of digital electronics, where digital electronics are low power electronics, usually on the order of millivolts or less than watts, and whereas power electronics is along the lines of high transmission power lines and this sort of thing. The Strange Story of the Quantum by B. Hoffman. Great Ideas and Theories of Modern Cosmology by Jagjit Singh. The Theories of Genes, Eddington, Milton, Kant, Bondi, Gold, Newton, Einstein, Gamow, Howe, Dirac, Kuiper, Hubble, Weizsäcker, and many others. Great Ideas of Modern Mathematics, Jagjit Singh. Now, another thing is Motz and Weaver wrote some great histories of mathematics and histories of science. So if you really just want a book that encapsulates the history of mathematics and the history of science, I would recommend Motz and Weaver and Carl Boyer's Conceptions of the Development of the Calculus. So anyways, this is just reflecting that in the catalog of Dover books, that pretty much anything and many things rather that were really good and went out of print, Dover picked them up and reprint them. It's always good to go to the source sometimes. Meaning if you can go to the originary work, sometimes it's a little bit more raw, it's a little bit more authentic, and the other times then after the developments are made and the derivations are as so refined, then it's harder to gather what was the thinking that went into the developments. So a lot of times the engineers and physicists' intuitions go into making developments, and then by the time you get it formally in mathematics, it's kind of watered down, as it were. Although it's safer and equipped and otherwise formalized, it's just a good idea sometime to go to the originals to read their things. Enrico Fermi, thermodynamics. After Fourier, there's Dirac and Pauli, and then there's Fermi. All right then. Well, thanks for taking a moment with me to leaf through some of the catalog of some of these fundamentals in books in mathematics and science and as of the day, and for engineering, which is a much larger book full of all these formulas that finally print out the values, resulting in a much smaller book, which is a table of the values according to the formulas, resulting into a calculator function in an Excel spreadsheet of sorts. So I wish you a great day, and hopefully more tomorrow. So long.